definition of an advanced material, of which you would include graphene, is a little bit woolly, but generally it's something that doesn't have an established supply chain, and is often being driven by the people producing that material, and they're trying all of their might to find a use for that material. So there's actually more than you might think. So there's some quite well-known examples of Ford Motor Company, for example, now using it across a lot of their fleet of new cars in composites. They're printing biosensors in Taiwan by the millions for glucose monitoring using graphene inks. There's a whole raft of companies in the battery supply chain that are supposedly using it as conductive additives. So it's out there. They're not necessarily the most thrilling uses of graphene that we might have heard of, but it's being used in reasonable quantities. Yeah. I always think of the word graphene being a little bit like the word plastic. So there's obviously many different types of plastic. Different plastics have different uses, and the person asking the question, I guess, knows that. So when it comes to choice, again, it's a lot of it is done empirically through experimentation. So taking materials from suppliers A, B, and C, trying it in your application, see which one works. I think we're a little bit cleverer than that now. The level of understanding, not just in individual people, groups, or companies, but in the community as a whole, has grown quite a lot over the last few years. An understanding of which of the perhaps 15 properties of graphene are important for which applications, and I guess which ones are not. We work with a number of patent attorneys to kind of assess that on a case-by-case basis, because there's so much coming out all the time that even if you look 1 year and then take 12 months later, there's usually quite a few, well, there's almost always a number of patents that have come out in that time. So it really has to be done on a case-by-case basis, but we're in order in the many tens of thousands worldwide. So it's one of the trickier things to navigate, I would say, when you're trying to work with commercial applications. What we've found is, and we've learned this through not trial and error, but through making the mistake, is that once you lose the hands that have created whatever the technology is, it's really, really hard to catch up. So I think having people who are academics and interested in an academic career track, working alongside the people that are picking it up for a period of months, is really key to transfer that knowledge. So having spaces where those people can work side by side is key. So I think it comes down to several things. So one is making sure that you've got a really good product market fit. And oftentimes people are trying to solve problems that have either been solved by another material already, or are not really challenges that people are really trying to solve. Having a really close working relationship, or as close as possible, with the end users, and really sitting down and trying to understand what challenges you're trying to solve early on is critical, really, in order to commercialize it and drive it through to mass market. It would depend a little bit in which form. Generally, I would say no. I mean, graphene is not a million miles removed from graphite, and graphite obviously sits under the ground for perhaps millions of years. So, but it doesn't oxidize, which is a common form of issue readily. So as a powder state, it will tend to reagglomerate a bit over time if it's a powder. For graphene inks, you certainly will get a certain amount of settling of the inks. They're not, but that will be the case for many inks used by industry. That would be as simple as making sure that you agitate or mix it up again before use. Some of the derivatives are a little bit more prone to decay, for want of a better word. So if you've got hydrogenated graphene or graphane, fluorinated graphene, graphene oxide, they tend to not be greatly stable at high temperature, which would be an issue in some applications, but in terms of shelf life, it's not usually seen as an issue. I think it's been shown over the last couple of years to be very scalable. So it's predominantly the people that are producing large quantities of graphene. They have shareholders or owners. They presumably looked at the economics of it and assessed that it's viable. Increasingly, we're seeing it being produced using methods that have already been scaled for other things. So there's not really a huge worry there. Graphite has a market price somewhere between $1 and $10 per kilo, depending on the grade. And that's going to be your absolute base price, and then it's a case of how efficient and cheap you can make your manufacturing steps in order to turn it into graphene. So if you look at there are companies selling graphene at $10 a kilo, which is pretty, I would say very acceptable price for, it's getting comparable to the plastic that you're putting it into if you're doing a composite. It's certainly cheaper than a lot of the other materials you might be using, conductive inks like silver, copper, those kind of things. I think the areas of sort of photonics and optoelectronics are really interesting. There's a number of companies. We've got Empyrean in the UK. There's new companies spinning out of places in Europe which are creating optoelectronic sensors which are, have a real defining edge over the competition, so over semiconductors, in terms of their performance, their sensitivity, requirements for other things like cooling, for example. And I know there's a really big interest from some quite big players in those kind of technologies. We've thought long and hard about how we can help deliver on that, the kind of application areas or kind of applications that we can perhaps impact. So if you think around things like lightweighting of any structures that are moving, so cars, aeroplanes, all those things, the less mass you're moving, the less energy you're using, and so on. Areas like infrastructure and the built environment. So concrete is a good example of that. There's a lot of people using additives like graphene to improve the compressive strength, the torsional strength, and so on. So you can get away with using less concrete. And concrete is a huge source of CO2. Both in moving it around from place to place and naturally generating CO2 as part of the process. So people are looking at graphene alongside things like geopolymer concrete as solutions to that. So there's a big program of work going in looking at that, and it's not something we're directly involved with at the Geek. So the Graphene Flagship, this big European program over 10 years, is one of their kind of work packages is to look at this. So I think nothing has been found to suggest that it's really nasty, really bad. But there are certain cases where, if you're getting it into in vivo and things, that it would be of a concern. I think generally it's very unlikely that graphene is being used in isolation in the outside world at all. And I think there's various studies where they've looked at, for example, if you're using it in a composite or an ink, that is, if that is worn away or rubbed away, that it's not coming off as free particles, which would be the danger. Yeah, so obviously a lot of stuff is bound under confidentiality agreements, but some of the stuff to do with printed sensors that we've got coming through now, using those in, embedding those within structures, within mobile structures, is really interesting, and it's kind of starting to sort of deliver on the promise of printed electronics. You know, wireless communication, arrays of sensors, you know, telling you all these different things about, you know, the health and performance of structures. We see it's a big trend in, you know, the biggest companies as well, but it's probably one of the more exciting areas that we're working on, that I'm involved with. Boronitride, for example, I mean, if you want a thermally conductive composite or a thermally conductive layer that you might print, but you need to be electrically insulating, of course graphene can't do that. So understanding where the advantages of one lie and done is something that we're looking at. Lithium disulfide membranes is a project that I'm involved with, and they have certain advantages over graphene oxide membranes, for example. But yeah, there's a number of those being commercialized. So of course, if you're talking about shrinking, you know, down beyond 7 or 5 something nanometer nodes, you start hitting material limits that are pretty difficult to overcome. But graphene is also going to have some challenges down at that level as well. So yeah, I think really is the best to say is graphene can work in tandem, as it does with in things like photonics and optoelectronic sensors. I'm not sure it's ever going to replace conventional silicon electronics for the kind of things it's used for at the minute, not within a short time scale anyway. Yeah, again, so it's something that we work on the edge of, but not directly on. I'm aware of probably 4 or 5 projects that seem to be quite promising for that purpose, talking about, you know, sort of 15-minute detection, high sensitivity. There, generally, you're looking at using the graphene as a very sensitive readout mechanism, and use it in combination with some you know, sensing molecules, for want of a better word, that you're attaching to the surface, and that's being used in many other areas, gas sensing and sensing of different analytes and things. But yeah, it does seem to be something that is you know, on the edge of being released, from what I hear. Yes, very easily. There's this well-known or reasonably well-known picture of, you know, an elephant sitting on a pencil, which is based on a you know, calculations done on perfect graphene and so on. The thing I always thought of as you know, being super strong is spider webs. Right? Everyone knows you can break a spider web, so it's strong for the size and thickness that you have, and that's obviously very important when you're talking about improving the strength of structures and so on. But on an individual level, yes, it's very easy. Yeah, so this interesting work, if you put it into a much stronger, we call it matrix material, much stronger host material, you can get the effective strength of graphene is much greater, so and much closer to its real value. So yeah, I mean, you could imagine having some sort of alloy with graphene dispersed in it. You could think about improving things like hardness, wear resistance, as well as the intrinsic strength. So, of course, other people are using, not in metals, but graphene combined with certain polymers and some ceramics to make kind of protection against bullets and ballistics. And they seem to be making some progress in that front. So, yeah, I don't see why not. I think, you know, we're really kind of at a tipping point now where we're seeing the applications where there is a real benefit of using graphene are kind of coming to the front. And I think while the majority of the populace won't necessarily be aware of it, it will be affecting, everyday lives of a lot of people. So yeah, force for good.